Let's start with something simple. We had something like now, if I wanted to parametricize this, write this in terms of parametric equations. It's just a fun verb. There are many, many different ways I could do this. The most simplest way would be to say x is t. And then, of course, y would be t. Yeah, once I say x is t, y is t to the fourth. That's one way to do it. I could also say x is t squared. And then y would be t squared. You guys semi with me here? I could also say x is, let's see if you guys have the list. X is t plus 4. And incredibly enough, y would be t plus 4 to the 4th. I mean, so whatever I make x, y is going to be the 4th power of that. Good Lord. This whole wall is moving.
So wait, what do you mean by that? Like y is to, you just put y to the 4th?
It's given to me. It's given to me that y equals x to the 4th. That's just the fact. Here it is. And then they say, make parametric equations out of this. How many possible answers are there to that? An infinite number of answers. Right? Yeah.
I'll get the second one.
Oh, what am I thinking?
Is that why I don't get it?
Yeah, if x is t squared, then y is the other way. Then y would be t to the 8th. Thank you.
All right.
My brain went the other way.
That's what I was.
Yeah. No, it's just incorrect. Yeah.
Would the graphs of the parametric equations still be a parabola?
They have to be. Yeah. In fact, no matter how you parametricize this, they have to be equivalent graphs because they're all represented the same shape. Just sometimes there might be one way to describe it or another that's easier to work with. This is a very basic example, so there's really not that many truly different ways to do it. Right? What about, I think they have a few like this. No, they don't. That's freaky. Yeah, they don't like going the other way. That's too bad. So they don't like doing this from this book for some reason. But this, you see this a lot. You see, you're given an equation, then you have to kind of write it in parametric terms. You'll see that in later calculus courses. I thought for sure it'd be in here, but it doesn't look like it is. What you guys will see will be something like this. Here's a nice one. Can you rewrite that? Can you eliminate the t between those? How would you eliminate the t between those? Even more directly. If x is t squared and y is t squared squared plus 1. So you could always tear it down and solve for t. That leads to some possible trouble, though, that you might not want to introduce, because then you have to put a plus or minus in there, and so. But it's going to square anyway away. But if I can find a direct route, if I can find this living in this guy somewhere, then that's easy. Then this becomes y equals x squared plus 1. So this set of parametric equations would describe this problem. Okay, cool. So see a bunch of problems like this, where you have to eliminate the t. And they also ask you to graph this. They're going to give you a range, possibly. Nope, here they don't give you a range. They just let you go to town. So the funky thing about this set of equations, I got this from number 8. I'll give you a clue on this. They kind of asked you, part A says to graph it, and part B says to write it in terms of rectangular. I would switch the order of these, obviously. Because if you first put it in, say, rectangular, you have an idea what this thing looks like. You know what to expect when you go to make your T, X, Y tables to graph it. Cool. So here, I'm going to give you a complete problem to try out. Maybe I'll even give you one with a little tree in it.
Why does the book put it, it seems like several times throughout the semester, it's easier, it's not just your preference, it's like, oh yeah, it's obviously easier to see steps. Why is it that the book consistently puts stuff in harder to easy order?
I wish I could answer that question. To me, it always happened in physics. I'd always answer part B before I answer part A because I use part B's results in A, if you've ever taken a class like that. Where it's consistently like that. Physics is a good one for that. Math and these kind of things is a good one for that.
Yeah, it's going several times, that's what I'm wondering. Like,
This one, it's not impossible to do part A, obviously. You certainly can graph this, but it's just easier to do part B first. And since the book or me or the nothing would realize what you did first. So what the hell? Why wouldn't I do that first?
So the publishers would comment somewhere in the 17,000 edition.
I know. You'd think so. But then, instructors like me have to actually call them and say, hey, and I just haven't. So it's all on me. So here, try out number, this is page 569. Let's see. Number 14. And just to kind of go off of what I just said, I know part A for them is graph, but how would you eliminate the t variable between these two things?
First isolate?
All right, so that's one approach. I could take, how would I solve this for t? Yeah, divide by 2, inverse cosine. And then I can plug that in there.
Is that substitution?
Yep. And that's always your go-to process if you have no idea what else might work. So by saying that, hopefully some of you guys are picking up on, there are very often simpler things that will work. This is always your, I don't see what the hell else to do, let me just do this because I know it's going to get me somewhere. Because I'm not really done here, truly. I can simplify this. Oh shit, this looks like a problem from that last freaking test. What do I do here? Yeah, what can I do from this? Draw a triangle. Right, where's x? Where's 2? So x here, 2 there, because it's cosine. What's this side going to be then? I like that y. But in terms of 2 and x, square root of 4 minus x squared, right? Pythagorean theorem. So y equals 3. Sine of this would be what? What's the sine of this?
Root 4 minus x squared over 2.
Yeah, that x piece over the hypotenuse. Now that really wasn't all that difficult, right? The thing that this does not capture, though, is, and actually I could put it right here, I don't know if, well, x itself could be negative, but then this could be plus or minus. Doesn't really capture that. So a safer route to go. Does somebody have another possible way I could possibly kill the t between these two? Something with identities, I'm sure. What if I squared both of these first? Because then what's cosine squared, for example? Yeah, 1 minus sine squared. And 1 minus sine squared is y squared over 9. Oh, yeah. 1 minus, are you guys cool with that? If I just solve this for sine squared, I get y squared over 9. Of course, future you can't see that. And now I can simplify this however much I want to. Believe it or not, these two are equivalent. I can multiply by 9 just to make this easier to look at. Add this over, what's it look like? Not a circle. The coefficients aren't the same, so that would be an ellipse. Yeah. Isn't that cool? I can try to solve for y. Divide by 4. Take the square root. Can I take a 3 out? Square root of 9 is 3. And this will be 1 minus 1/4 x squared. And I can simplify that down to become that. I can make this 4/4. The over 4 becomes over 2. I mean, that's just going to become that. Can you guys see that? I'm running out of interest and board. This is not too hard to get from there to there. But this is just, I mean, that was pretty quick. But I just want to always show you there's more than one way to do this. And sometimes another way will be much quicker than the first thing that comes to mind, which is just straight up substitution. Okay, so coming back, that's trying to solve, and this actually has the plus or minus part that's missing if you kind of do this directly. So to tell you honestly, I would stop around here. Maybe add the 4y squared, because then it's obviously an ellipse. When I say it's obviously an ellipse, is it not obvious to anybody? You can be very honest. A circle would have the same coefficients here, so it could be 4 and 4, because that just means if I divide by 4, I get a radius of 1/2. So as long as these two coefficients are the same, that's a circle. The minute they're different, that means it's not symmetric anymore in both directions, so that would be an ellipse, squished in one way or the other. Or stretched out, if you like that better. Alright, so coming back to graphing. Now it's just where you have to make tables and graph what the results. We kind of know what it should look like. It should look at a piece of an ellipse, or maybe the whole ellipse. We are going 0 to 2 pi, so maybe we're going to pick up the whole thing. So this is have these trig functions. We have the same basic stuff we can always throw in. I've got 0. So what do you get for x here? Yeah, 2. Good. Let's just give you all the cosines here. At pi over 6 now, it's going to be 2 root 3 over 2, so the root 3. Pi over 4, it's root 2 over 2 times 2 is root 2. 1/2 times 2 is 1, and then 0. And then here I'm just going to get The reverse of that. Alright, he's going. Deal with it elsewhere. Here, this is going to be 0. 3 halves, because it would be 1 half at 30 degrees. Root 2 over 2, so it would be 3 root 2 over 2. Then root 3 over 2. And then finally, it's going to be a full 3. Don't worry, it does that. So if I graph, crappy little graph here.
So you would mark points off, you would just graph 0, pi over 2, pi, 3 pi over 2, and
well, the nice thing is, and I'm glad you said that, if you do this part first, you can see that it's an ellipse. And then you're a little bit more sure about this shape. If you're not sure what this thing's supposed to, if you do the elimination of t and you get something like this, what does that look like? I have no freaking clue. So then I'm going to want to do more inputs. But here, if I do this first, I know it's an ellipse. So you're perfectly right. I can do some extremes. I know it's supposed to be an ellipse. But here, so what do I got to get? Now I focus on xy. 2, 0. Root 3 is like, what is that? 1.7 something. 3 halves. Root 2 is 1.4. And then 3 root 2, 2.1, I think.
2.12.
Yeah. And then 3 root 3 over 2 would be like 2.4 maybe? I'm close. And then 0 is 3. So my ellipse is looking like it's had a rough day. And since you know it's an ellipse, you know you're going to repeat these same values back here, down here. Then you got your ellipse. You can see that 0 to 2 pi. It's a full rotation around. So that's really kind of cool. The equation for an ellipse in parametric form is kind of simple. It's also simple there too, so what the hell. Okay. So it doesn't get into anything too different from that. You can get some really cool shapes, like on page 570, number 56. Yeah.
With that, the coefficients seem to correlate with the axes. Could you just do it like that if you wanted to?
Now you can start making some generalizations. Now that's the beauty of mathematics. You start thinking about patterns. If that would have been a 4 instead of a 2, then obviously what would have changed?
The height and the depth.
What would change is that was a 4 instead of a 2.
Wider.
Good. It would have been a little wider.
Yeah.
So, but before we did this, I doubt that any of you really had a good feel for what that was going to do, but now you can see the direct relationship it has. And of course it makes sense, because what's x itself going to do? If cosine goes through its whole cycle, what's x going to do? Go from -2 to 2. In a very prescribed manner, because cosine is nice, fluid motion. And the same thing's going to happen with y. It's going to go from -3 to 3. So we can see the range is -3 to 3. The domain is -2 to 2.
Doesn't it have something to do with the foci or whatever too? Like the angles? I don't know.
Eventually, yes. For this equation, no.
No?
Yeah, but the foci do come into play. Yeah, later. Not for right now. So, you start getting some, you guys all have anybody have your graphing calculators? Take that bad boy out. Let's try some parametric stuff. You need to borrow one? What exactly is t? Well, it's sort of like when I first start teaching my algebra students how to graph, y equals 3x minus 2. And we make an xy table, and they could just ask, the same way. They can say, well, what's x, John? What would you tell an algebra student if they asked you what is x? What is x here?
The variable.
So you can say it a few different ways. Good. It's the values along the horizontal axis.
Where's the t-axis?
It's the input variable, right? Some number, any number it wants to be, right?
Don't ask, just plug into it.
Don't ask, just accept what I tell you what it is. Shut up and sit down.
It's time.
That's what I normally tell my students. Just accept it and go. So your answer to your question is, what's t? It's kind of the same thing, except now t is driving both x and y. Here, x is driving y. Period. Now we're getting into the point where I've got one input variable driving two output variables, x and y. When we graph it, t is behind the scenes, as it often is in real life. I mean, you see something moving around and you have this velocity up, velocity over. Let's take out the third dimension for a second. You with me? So as it changes its velocity, it's this background thing affecting where I can actually see it. So my field of vision is x, y. But behind all of it, there's some other variable possibly controlling that thing's motion, right? Are you kind of with me? A little bit. All right. What was 43? This looked kind of funky. Try to graph that in your graphing calculator. Now, most of you are probably on what mode? Polar. Yeah, so go down and change it to parametric. And make sure you're in radians also. So now when you go to y equals, it should show you x1t, y1t. Question? I love it. So go to your window. You should see a T min, T max. So 0, 2, 5. Gotta love that shit. Now, there's a T step.
Sounds like a dance move.
Are you guys with me? So has everybody got this put into x1, y1? Okay, now, you look at your window. It's got T min, make that 0. It's got T max, we can make that 2 pi, 6.28 with that. T step, who remembers what a good step is for a radian measure? We've done this a few times. Like 0.13 is the one that the calculator normally kind of does, just always. And that was like pi divided by 24. It's not a bad step. So we can do 0.13, why the hell not? Now we got to have some idea of what the possible outputs are. And of course, sine of whatever is going to be in between -1 and 1. So I can put -1 for x min. So put -2 and 2 just to give it room to play. F scale is just how many tick marks, so you can leave that as 1. Don't worry about that. And y min and max, it's also a cosine of something. It's a trick, so I can just leave that as -2 to 2. Is everybody with me on that? So you have to have an idea of the domain and range, the intervals that define x and y values. So you can kind of set up your x min, y min, x max, y max. Say again? Let's see. Oh, that's cool. Look at that's funky. Yeah, you're right. I might want to zoom in a little bit because it gets a little busy. Have you guys hit graph yet?
Oh, yeah.
Can you give me an idea what it looks like? Sort of. I got mine going around.
Do it back.
So if I zoom in a little bit.
Looks like a doctor's signature.
Exactly, yeah. Let's make our Go back and make your t-step 0.05. Let's see if we can make this a little bit nicer. Yeah, just a little bit. Now that's interesting. Now it kind of goes back and it's picking up a lot of what we missed by having too large of a step.
Is that what's kind of flat on the bottom?
So mine looks like that. Whoa. Why is your stop there?
Ours isn't.
Because I can't think that much.
0 to 2 pi. Let me see. Is it still thinking?
No, that's how it was looking.
Oh, 0.05. Yeah, 0.05. That's right. Negative 2 to 2.
Is your XY scale? Are you in agreement?
Yeah, no.
Get out of memory.
That's weird. Why can't yours do it? It's funky. Somebody else have one that's got like crazy? What does most of yours look? Yeah, yours is crazy. I'm with you on that.
Same thing.
0.6. No.
That's just funky. And you can imagine when you have trig functions as inputs for other trig functions, you get craziness like this because the outputs for this are going to be between -1 and 1, right? But it's -1 and 1 radians for sine. So this is not going to go through its whole cycle. It's not going to go from 0 to 2 pi. So it's going to be possibly some quick turns. And then this t to the 3/2 thing is going to be kind of funky for an input in radians to the 3/2 power. So it's a good sign about not making your step too big, because then you might miss the intermediate turns it's making. If you make your step too big, it's just going to calculate it at certain points and connect the dots. Because resolution isn't high enough, you're going to miss some stuff. You guys want to take a break?
Yeah.
That's all you got to say. Come back in like 10 minutes. 35 after.
Yeah.